Hello, folks, and welcome to Rational Science. Today we're going to be talking about quarks. Now, I think all of you have heard more or less about quarks. Neutrons and protons have three of them, and you always paint them as balls. The quarks and the neutrons and the protons are all balls. Now, here's the first challenge for you today to think about that. You take three balls, and I want you to tell me how you can make one ball out of three balls. Okay? I say it can't be done. You can make a triangle, more or less, but you can't make three balls. You can't make one ball out of three balls. Okay? So that's the first challenge. But in order to understand what the quarks are, just like neutrino the other day, you need to get into the mind of a mathematician. Mathemagician, because they do everything by magic. Okay? And for this, we've got to go through a little procedure so that you can get inside the mind of a mathematician. Okay? I want you to understand how a mathematician thinks, because that's going to tell us a lot about how quantum developed and how we ended up with neutrinos and quarks, as well as protons and neutrons. Okay, so here goes. A mathematician goes to the lab, right? He observes something. He observes something invisible. In other words, he doesn't observe, not with his eyes. He sees something happening in there, and he might see some things that are visible, but he doesn't see the invisible forces at work, or mechanisms at work, or agents, Mother Nature's secret agents. He can't see those. He's got to infer those. And a mathematician always infers everything as a particle. Why? Because particle is not a particle. A particle is a number that he can put in an equation. Okay, so you have to understand that as a minimum. There are no particles in quantum mechanics. In other words, they call it a particle theory. It's not. It's not a speck of dust type of theory. It's not a little ball, little bead theory. It's a numbers theory, meaning it's not a theory, it's a description. So it's a numbers description, which they call theory. Okay, and so he goes in there, he goes to the lab, and he sees something visible. And now he's got to figure out what happened there, what invisible forces acted in there. And he goes back to his office. Now he's got to do some calculations. He's going to look at how fast something went, what force, how much mass it might have. Okay, these are the issues that concern a mathematician. Okay, so he goes in there and he sees something, and he puts his first equation. He says A equals B. Okay, but it turns out that B has some parameters, has some properties. Okay, so he's going to go in there and he says, okay, it's got charge, which was invented, by Mr. Ben Franklin, the positive and negative. So he's going to give this one a positive charge, and he's going to say, well, it's got a lot of mass, and he might say that it's got a spin, whatever spin is. Because a top can spin maybe clockwise or counterclockwise. He can't deal with that because that's qualitative. He needs to put a number to these things. So he says, well, that's a spin plus one. Okay, and I hope you like my hieroglyphics. I hope you learned them by heart. Okay, these are very high level hieroglyphics, so it's very important to understand those signs. Okay. And then he goes in there and he puts another variable or another, could be a constant also, but he puts another factor in there, okay? He's going to call it C, okay? And it turns out that this C also has some parameters, but they're a little different. One might have a negative sign, for example. It's got maybe low mass, very low mass, and it could have a spin in the opposite direction. So he's not going to say it's counterclockwise. He's going to say, well, that's a -1 spin. Okay, So now I hope you keep track of these. It's going to get a little complicated, okay? And also, it'll be on the test on Friday, so you better memorize them. Okay, so now he needs to put another variable because he observes something in there that is not accounted by these two variables, B and C. So he said, well, something else happened in there, and I can't account for that. So what do? Well, what I do is create another variable. And this variable could be anything. It could be energy. He turns that energy into mass, which means particle, which means what? Little ball, which does not mean a little speck of dust. It just means a number. So that's what it is. That's what it's going to be in his equation. So he calls it D, okay? Turns out that this one has a charge of 0. He's got to make it so because he notices that if he puts a negative or a positive in there where it's a 0 charge, well, it's going to create a problem because you can't have two positives and one negative or two negatives and one positive because then the equation would not, check out. So he goes in there, he said, well, it's got to have a positive, it's got to have a 0 charge. And maybe it's got a little bit of mass because he's got to account for the energy in his system. So he says, well, it has a little bit of mass. And so it doesn't have large mass or it doesn't have no mass. It just has a little bit of mass. That's what he needs in his equation. So that's what he puts in there. It's not that he found a particle out there. It's that he makes the particle out of nowhere to make his equation come out right. That's all it is. And maybe he determines that this particle has no spin. And I don't know how a top cannot have spin. It either spins or doesn't spin. What does it mean that it doesn't have spin? And again, you have to understand that there is no such thing as spin in quantum mechanics. There is no notion of spin such as what a top does. You spin a top, and we all understand what that means. Or you talk about the spinning earth, and we all understand that. That's not what spin is in quantum mechanics. In quantum mechanics, it's a very totally different animal, and they don't have a definition for it, not a physical interpretation of what spin is. That's why they have to put the +1 and -1s in there. It's like if you mark the top with a little check mark, with a little, you mark it maybe with your marker, or maybe you cut a little groove in it, and you spin the top. When the top falls down and it's showing the check mark in your face, you call that a 1. If the top spins and the check mark or the little mark is on the opposite side of your eyes that you can't see it, we'll call that a -1. And if it's to the left or to the right, you can call it a -1/2 or a +1/2 spin. That's more or less the notion that these people have of spin. So spin, first, has not been defined in physical terms. They don't have the slightest a clue what they mean by spin. That's the first issue. The second one is that they have these numbers for these spins, okay? So spin is not what you think spin is, just like particle is not what a particle is, okay? They use these words and they're euphemisms for what they really mean. Okay, so they go in there and they find out that that something else is happening in there. Okay, the mathematician goes in there. He can't figure out that there's another phenomenon going in there that he cannot explain. And he says, oh, what about this? And so he puts another variable. He invents another particle, and this one has no charge and it has to have no mass because that's what he observes in the lab. In other words, he says, well, the energy stayed the same, so that means the mass is the same. That means this particle, E, does not have mass. And maybe it can't have charge, because if it has charge, then he's got to invent another particle to counteract it. So if he puts a negative or a positive under the E charge, well, he's going to have to invent another particle that counteracts that one. So far at this point, he says, well, no, it's got no charge, it's got no mass, and maybe the spin is, I don't know, up and down, and he calls that maybe, a half spin, okay? And you might say, well, where did he get this particle? I mean, was that inside the atom, or where did it come from? And the answer is, it came from heaven, okay? So that's where it came from. He calls this heaven vacuum or false vacuum, or he says the seething energy that's in the space all around the collider, the collider that he used to accelerate this particle. So he calls this heaven because this is going to be magic at this point. He says, well, it comes from the vacuum, and this way he covers he kills two birds with one stone. He covers two bases. On the one hand, he proves that the vacuum is made of something, out of mass, out of energy, out of whatever you want to call it, virtual particles, and they come in from the void for whatever reason. They donate their charge, their mass, their spin, whatever they have, and they immediately, within a microsecond, go back to form part of space. Okay, so he gets this particle out of nowhere because he can't include it inside the atom. If he does, then he's got to account for the energy of the atom. He's got to account for the charge of the atom. He wants to avoid all that. He said, no, it came out of nowhere, and he solved the problem. Okay, so this is how they do it. Okay, and then there's another particle maybe he can't account for, and where did this one come from? Well, I would think that this one came from hell, right? Maybe. Okay, so this is how they do it. Okay, they just invent these particles, and they have to invent them in order to account for observations, what they call observations, meaning that they observe something visible, but they can't see the invisible stuff, and it's the invisible stuff that they have to infer. It's these forces that they have to create, and they have to give values to each one of these parameters, such as charge, mass, spin, for each one of these variables that they introduce. This is how they've created all these particles, throughout the last 100 years. Okay, but then comes the issue of proof. Okay, you got to prove whether this particle really exists, or whether it's just a mathematical, contraption. Is this just a hocus pocus, mathematical hocus pocus, or is this some real thing that's inside the atom? And so for that, they have to go to the lab, and this is when they start, they start colliding particles, or so they think. This is what they think they're doing. Okay, and you can see that each one of these traces, whether it's a straight line or a squiggly line, it doesn't matter. They think it's a particle that's moving in there, and what you're looking at really is a trace. Okay, so whether you look at the curlicues or you look at the straight lines, you're talking about particle traces, because they think that what they're doing is smashing particles, and this is the debris. This is what comes out of the hand grenade after it exploded. Okay, this is what comes out of ground zero, and they say, okay, I saw this particle go that way, that went over that way, and what they think they're looking at are traces of these particles through the environment, which is usually a gas, usually hydrogen gas, but they have other gases, I think, as well. They've tried different gases in there. Okay, so what sense can you make out of this? Well, what they say is they go in there and they say, well, hold it. Here you have two particles, okay? If I can get it up here, particle A and particle B. And you can say, okay, particle A went farther than particle B. Then these two particles have different energies. And energy is a different way of saying mass according to Einstein's famous equation, E equals mc squared. So all they have to do is a little calculation of saying, okay, I use so much energy to accelerate these particles, or they take up so much energy, or so much energy was introduced into the system to get this particle to go this far and the other one to go that far. And so what they do a little calculation. They say, oh, particle A has a different mass than particle B. And they go in there and calculate these masses based on, first, the curvature, second, the distance, okay, and then the energy that they use to move them to the places where they're at, okay? And they do something similar with charge, okay? So here's charge. Give me a second here. C and D, okay? And so you see a curlicue on C and another curlicue on D. What, let's assume, goes clockwise, the other one goes counterclockwise. Okay, so they say, okay, this one is a positron, or a positive electron, the other one is a negative electron, for example. Okay, and so what they do is they give negativity to the spin, to the charge, because it depends on which way they're spinning. If they're spinning clockwise, they could be negative charge. If they're going counterclockwise, they're positive charge. And this is essentially how they do it. Okay. And here's an example from real life. Okay, this man, his name was Carl Anderson. He won the Nobel Prize. Let me put him over here and get back in here into the picture if I can. Okay, and he discovered or found, or whatever you want to call it, made exist the suppositron. They call it the positron. I call it the suppositron because Mr. Anderson made a supposition. That's what he did. His supposition was that that particle went from south to north and it went towards the left. So he says, that's not a negative particle. That's a positive particle because it's going in that direction. And you have these magnets in there, and they should have taken the particle in the opposite direction. Since it went into the left instead of to the right, that's a positive particle. He thinks that's a trace, and so he says that's the trace of a positive particle, and he's going to call that the positron, the one that they were looking for. And so that's how he proved the existence of the positron and got a Nobel for that. Okay, so that's how these things typically work. Okay, and so this is what they think is happening. They think it's they're colliding. They're sending these particles, which they ionize. In other words, they think they're removing an electron from an atom. Okay. There's a process for that. We used to do it in the semiconductor industry. We do it by having a canister with some gas in there. Typically, you remove an electron, or so they think that's what's happening. The ion is positively charged, and now you can move it down the beamline with magnets because you can manipulate it. Okay, that's the idea behind this. Okay, and this is the same thing that they do at CERN and Fermilab and SLAC and Brookhaven and so on. Okay, and so this is what they think is happening. They're thinking that they're shooting bullets at each other when those particles collide. They have one going in one direction, one group of particles going in one direction, the other one in the other direction, as you see on the upper left there. And then they collide them, as you see on the upper right. Okay, so these particles are shooting at each other. They make them collide. Okay, explode, and then they look at the debris, which is what you saw just a second ago on the traces. What we think is happening is something different. We think under the rope model, what you have is throughout the beamline, you have these atoms. Really, could be atoms, could be molecules, okay? And they're all bound to each other. They're all merged. Their electron shells are merged into each other, and what they're doing is they're oscillating in place. In other words, they're torquing. The whole serpentine, as we call them, are torquing. So it's a difference between putting two drills against each other versus two guns against each other. There's a difference in the mechanism we're proposing for what's happening inside a beamline. Okay. So this is where they get the idea of particles. Okay. So what is the issue? The issue is that here, when you see these charges go in different directions, they think it's particles that are causing some kind of trace in a squiggly trace. And the problem I have with this is that, these things are going, according to them, close to the speed of light. And the question is, can something going at the speed of light go in such closed curves as you see there, or in the one that you saw for Anderson? These particles are going very fast. And the question is, can a particle make such closed loops at the velocity of light or near the velocity of light? So that's one issue you got to ponder, whether that's possible. And so here's the So that's essentially the issue. The issue is whether they are shooting particles, whether they are colliding particles, which is what they think they're doing. They think they're sending particles in opposite directions along this accelerator beamline, and that they're pointing the beams at each other, the rays at each other, and that the particles are colliding there. So it could be an atom, it could be a heavy atom like they've done it with gold. They ionize gold, they make the gold ions collide, and then they look at the debris, and what they see is tons of particles, certainly more than what are inside the nucleus of the gold atom, for example, quarks, and essentially, protons and neutrons made of quarks. So what they're looking at is quarks. And they have gluons in there that keep the quarks together. And they paint them as these elongated, bubble gums. That's what keeps the quarks from flying apart. But when they collide them, they get gazillions of particles. And they say, well, what we created is a gluon quark or quark gluon soup. They have all these particles, and they say, well, yeah, all those were inside the nucleus of the atom. You say, all those particles, gazillions? Because when you see the explosion in there, the photographs that they show, or the computer-generated images, what you see is these explosions with gazillions of traces. And you say, all those were inside the tiny atom? All those particles? And they say, yeah, because they're gluons and they're quarks, and so there's only 3 quarks per neutron and proton. In the case of the gold atom, it's like element number 84 or whatever. And so you can do the calculation. You're going to get maybe 200, 300 particles there. The rest are what, gluons, and what gluons are infinite because you get gazillion, you get thousands of particles or explosions there, debris. And so the question is, what are we looking at? What are we staring at? And they claim, yeah, that all those particles are inside the nucleus of an atom. And so they collide them, okay? And then again, you say, well, what did you collide? Did you collide a particle? And it turns out these particles are what? Are numbers. What they're colliding is numbers, because when you say, what does the quark look like? What does a proton look like? Does it look like a ball, like I just showed a minute ago, the 3 balls making one ball? Does it look like a ball? And they say, we don't know what they look like. So because they don't have a picture of what's inside an atom. Even with the atomic force microscope, which is the most powerful thing they have to look in there, they cannot tell you what an atom looks like, let alone what the nucleus looks like. They've never seen the little electron bead going around, which is what people think that these people saw. The laymen, they say, well, yeah, we know what an atom looks like because we've taken pictures of them. But when you look at the pictures, they're all, bird's eye views. You see a little ball at the end of that. They say, see all these little balls? Those are atoms. So we can see atoms. Well, if they're balls, are we staring at a little electron bead going around? Are we taking a picture of a film of a little bead going around? Is that what those balls, those images that we see, is that what we're seeing? Or are we staring at, what we say, which is a membrane, which is a little different than a little ball that's going around, a little bead that's going around, creating traces known as orbits, and the summation of which makes an orbital. Okay, so what are we staring at? And if they can't tell you, if they say, well, it's just a number, it's a number we put in an equation, then how can they be colliding numbers? So it's this duality of math and physics that constantly gets in the way of understanding. Okay, so let's recap from the other day what we had. Here we have a little history of what happened to the neutrino, especially. The original atom proposed by Rutherford and Bohr, and there you see it at the top. It's a little planetary atom, little electron bead going around the nucleus. Okay, so we all understand that. The only issue there is what keeps the electron bound to the proton. You got to account for that from a physical perspective. Mathematically, you can say whatever you want. You can say this one has negative charge, that one has positive charge. You can measure it and say this is 1.6 times 10 to the minus 19 coulombs. Fine, you can do all that stuff. The issue is, please make a movie or of your atom, or a picture of your atom. I want to see a picture of your atom. What are they going to put? And they have to put that atom because they have to explain ionization, they have to explain what you see there, quantum jump, and they have to explain electricity. And for those three phenomena, observations, they have to use this planetary atom. They have no choice. And that's what we use. When someone explains electricity to you, that's the atom he's going to use. So then you ask, is that your atom? Is that how the atom works? I mean, you have a little bead going around. And that's when they say, well, you got to take college quantum mechanics at the university level, very maybe master's degree or whatever level, to understand the atom. Yeah, because they're fooling you. They're saying that is not their atom. They deny that atom. Okay, and sometimes they get around to saying, well, that's not our atom, the planetary atom. Our atom means that the bead can be anywhere. Well, that's still the planetary atom. We're saying that there's a little bead next to a bowling ball. I don't care where the little electron bead is. Your atom is a bowling ball with a bead next to it, period. And if that's not your atom, tell me what is. And if that is your atom, tell me what keeps the electron bead bound to the proton. So that's where we start. We start on the wrong foot, and we still haven't changed that in 100 years. We still have the planetary atom in one way or another. And the only thing they have to explain there is the electron bead, why it remains faithful to the nucleus. Chadwick, around 1932, he discovers the neutron, and that was because, hydrogen, you would think that if you go to helium, which is element number 2, well, that should have 2 protons and 2 electrons. Straightforward, right? And it turns out that it did. When they ran that experiment there, they came up with this. Okay, Chadwick and his team. They found out that helium did not equal to 2 hydrogens, but rather to approximately 4 hydrogen atoms. It was 4, not 2. And they couldn't put charges in there, because if they put 2 more protons in there, then they would have 4 positive charges and 2 negative charges of the electrons. So they had to change that, and they say, okay, the guy that's in there has the mass, but it doesn't have the charge of the proton. And that's how the 2 neutrons went into the nucleus of the helium atom. Okay, so this is how the neutron came into being. Okay, then Pauli and first Pauli proposed it, but Fermi was the guy who wrote a paper in 1934, actually, or that's when he published it. And essentially, they came up with a neutrino, and I talked about that last week, to explain this beta decay. Okay, the energy simply did not add up. You had to account for the energies in the system. Okay, why it remained constant. And this is more or less what I showed the other day. Okay, so you can see it there. Okay, the explanation was that a neutron essentially gets rid of a boson, which was invented essentially eventually. Okay, the weak force. But his explanation, in other Fermi's explanation, was that there was some particle in there that caused beta decay, and when the electron was spat out, okay, there was this other particle called an antineutrino. And so he played around with the neutrinos and the electrons. The weak force, the W boson there, was invented later on as an intermediate step. So Fermi essentially went directly from the neutron to the neutrino electron. Okay, so he just did that calculation. Okay, and then obviously, then that was a mathematical trick, and the question was whether there was something more, whether that was real. Is there really a neutrino out there? The electron was a done deal, but the neutrino, was this invented just for an accounting process where you have to account for why the atom, when it decays, like a neutron converts into a proton and a proton converts into a neutron, inside especially a heavy atom. Okay, and they say, how does that happen? How does this transmutation, this morphing, this metamorphosis? And they say, well, it gets rid of the neutrino, or it acquires a neutrino or whatever. And so they had to account for that by putting the neutrino. The question was, that neutrino real? That was an accounting procedure. Now let's go to the lab and verify that there is a neutrino. That took them several years, okay? And they eventually came up with, in 1970, they were able to prove the neutrino, and there you see it, okay? They exploded another of those explosions inside the chamber. They say it's a collision, and they looked at the particle traces, and they looked at the masses, energy, all this stuff, the speed and distance, and all the stuff they have, all these parameters, and they calculated that one there had to be the neutrino, the one that was spat out by the system. Okay, but the funny thing about it was that they had to make the neutrino have no mass if it was part of the of the atom. Because if you have neutrinos with mass, you may run into trouble in there. But you got to change the mass of the proton or neutron. You have to change the mass of the nucleus. How many neutrinos are there? What do they weigh? Mass. how many particles are they made out of? Okay, that sort of thing. And so one of the ideas was that was proposed and for many years was that it came out of the void. It came out of the sky. Came out of heaven, vacuum heaven. You have to account for this particle, and they said, well, in the process, the neutrino is borrowed. It's a virtual particle borrowed from the vacuum momentarily just to get the equation to come out right. Then it goes back into the vacuum. That was the mechanism. It's called magic, quantum magic. Okay, so they discovered it eventually. Okay, they proven the existence of the neutrino, and they eventually ended up with all these neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. So they have all these different types of neutrinos, different flavors or whatever you want to call them. Okay, but what happened after Fermi published his paper in 1934? A lot of people began searching, and they said, well, hold it. The neutrino comes out of the atom or is borrowed from the vacuum, whatever theory you have, okay? But that doesn't explain some of the things that are going on inside the atom itself. You don't have the energy in there to justify what's going on inside the atom with the transmutation. And so they had to come up with something else. They said, look, this still doesn't account for why, for example, protons don't repel protons inside the nucleus, especially that. They say, okay, well, we're not done. There's a difference, because here we have Mr. Chadwick saying, look, there's something called a neutron. A neutrino is another particle that is not the neutron. There's a difference between them. And that's when the Japanese fellow, his name is Yukawa, he came up with a meson. Okay, the meson or whatever, however you want to pronounce that, and he invented that. And he said, well, it's at the time they had no idea of quarks, okay, but that's essentially what they ended up with. They say, look, we have a meson, which is this quark anti-quark pair, okay, and they have a strong interaction. And that's what he described mathematically, and that's what that's why Nobel smiled at him. Okay, and he says the following in his Nobel lecture. He says the interaction energy calculated on such assumption is much too small to account for the binding energies of neutrons and protons in the nucleus. Okay. The transition of a heavy particle from neutron state to proton state is not always accompanied by the emission of light particles, photons, right? A neutrino and an electron, but the energy liberated by the transition is taken up sometimes by another heavy particle. Okay, and that's where the meson came in. Okay, which in turn will be transformed from proton state into neutron state. Okay, so he was still trying to explain that transformation, and he says, look, there's another particle in there. Okay, and we're going to refer to these particles as mesons. Okay, so that's how the meson came into the language. Okay, but it took a few more years to come up with a quark notion. And they started playing with quarks, and they said, well, we have quarks, anti-quarks, and eventually, and they had all different combinations of quarks. Okay, they didn't have a name for it, but they had all these particles that they had in their minds that there's a couple particles in there, etc. And they put them in different combinations. They ended up eventually with three. Okay, the three quarks. Okay, so because they were able to not explain. Again, we don't have an explanation. What we have is a description, and these are all descriptions. That's why they're not theories. They're just descriptions. And so they said, well, by 1970, they were able to calculate, to figure out, that the neutrino was there. But then what happened? By 1960s, early 1960s, they began to play around with the quarks. They came up with these particles, which eventually were named quarks. Originally, in fact, Zweig, who was Russian, he was born in Russia, but he lived his entire life in the United States. So he studied and did his work in the United States. And in fact, he's still there. And he named them aces. Okay, there was a little fight with one of his mentors. His name was Murray Gell-Mann, and Murray got the Nobel eventually for the quarks and not Zweig. Why? Because they had two different types of notions of what quarks are. And in the case of Zweig, he's really the guy who came up with it, and he claims that he insinuates that he was robbed of the Nobel by Murray Gell-Mann. What happened was that Zweig went to Caltech, and he studied. He went to Gell-Mann and asked him to be his supervisor for his thesis. And Gell-Mann rejected him. I guess he had too much work or whatever. He said, "No, go and see Feynman." So, who was down the hall. And so Zweig went down the hall and asked Feynman to be his advisor, and Feynman agreed, and so they eventually became his supervisor. Okay, so what happened is Zweig started investigating. He went to the lab. He started looking at some of these collisions and doing his calculations, all that stuff, and he came up with the notion of quarks, essentially. And he discussed them with Gell-Mann and with Feynman constantly, for a couple of years. We're talking about maybe 62, 63, 64. By 1964, the idea came out that there were three of them that formed the neutron and the proton. Okay, so this is the idea that was emerging in there. The three balls that make one ball. Okay, and one of the issues there is that, and maybe that's why they gave the Nobel to Gell-Mann, is that there was an issue in the difference of what they were proposing. And I don't think Zweig got the hang of that, and maybe that's why he didn't get the Nobel. Okay, and it's that Gell-Mann had a notion of what is known as the current quark, whereas Zweig had the notion of a constituent quark. And the difference is that when you look at, if you look at those three quarks, the charm, the top, and the bottom, those are heavy. You look at the energies, you'll see they're all in the giga electron volt range, billion electron volts. Okay, and so there is no difference because these are heavy quarks. So there's no difference in their interactions. Why? Because the gluon field does not affect them as much as the gluon field affects the light quarks, such as the up, the down, and the strange. Okay, and so those are known as constituent quarks. What's happening here is they're looking at the interaction between these quarks inside the nucleus and inside the proton, inside the neutron, and how they interact with the gluon and who knows, the vacuum field, whatever's in the vacuum, all these virtual particles, all these virtual quarks that are flying around in space, I don't know. So they have all this interaction, and that interaction affects the constituent quarks more than it affects the current quarks. Okay? So this was a notion that they were developing. By 1964, we have this notion of a quark. And again, they give the Nobel Prize to Murray Gell-Mann because he's the guy who apparently figured out this key issue of the current quark. Or maybe it's just politics, as it usually is. Because he was, he was down the hall from Feynman, and Feynman had won his Nobel Prize in '65, and Gell-Mann, I don't know when he got his, but he got it shortly after that, because it's like, all these guys, they know each other, and they say, okay, if you vote for me today, I'll vote for you tomorrow. That's why they all have these prizes given to each other. They're all from the same club. Okay, and as long as they all repeat the same mantra, about quarks and so on, they're going to get their Nobels. Okay, so you got to stick with the catechism, the official catechism. You got to toe the party line. Okay, so what do we have? Well, we have that quark is really an accounting issue. We saw this the other day, and that's what it amounts to. There is no real quark in the sense that there is actually a particle there. They had to look for a particle that fit their preconceived notions. Okay, it was a foregone conclusion, and they had to find it no matter what. Like they're going to find dark matter, no matter what, they will find dark matter because they've already proven it in their minds. They have no other explanation for why, a galaxy rotates the way it does. And what they do, they sprinkle all this dark matter on the outskirts, and that's how they get the galaxy to spin the way it does, without the stars flying out, and with the ones on the outside going fast or faster than the ones on the inside. So the only way they explain that is by sprinkling mass on the outside, and they call that dark kilograms, dark matter. Okay, fine. Now they're looking for it in the accelerators, and believe me, they will find it. Someone will get a Nobel for discovering dark matter at CERN or wherever. Okay, but what they did was they had to. So it was an accounting issue. They had to explain why, for example, the proton had charge and the neutron did not, if they were made of quarks. How do you account for that? And so they said, well, it's simple. We're going to give 2/3 charge to the up quarks, and we're going to give a negative 1/3 charge to the down quark, whatever that means to you. Okay, so, and why? Because they need it for the accounting procedure only. Okay, that's the only reason for those numbers. And they say if you take two up quarks, 2/3 plus 2/3, and subtract a down quark of minus 1/3, well, you get one charge, which is the charge of the proton, which is the opposite of the charge of the electron. We're done. We understand that. Okay, the math. Okay, it matches. And then how about the neutron? Well, if you take 2/3 of an up quark and you subtract 2 1/3, negative 1/3, right, of a down quark, well, you get 0. And now you explain charge with that. Okay, and then they couldn't explain the mass part, but they had the neutrino, and they say, okay, the neutrino comes into the when the neutron decays to the proton, well, the neutrino enters the phenomena, the transaction, and either it's massless or the mass is borrowed from the vacuum, and we're done. It's just all magic. There's no explanation of the physical mechanism of how this works. It's just accounting. We need a negative charge here. We need a small mass there. That's what we put. We call that a particle, and we put it in the equation. That's only accounting. It has nothing to do with mechanisms. That's the point that I'm trying to make. Okay, so we ended up with a quark after all these years, and we didn't stop there. What we did, we went with the. We had to look at the forces as well. Okay, because one thing is the particles themselves that form what we call the matter particles. And the other one are these so-called forces, which are turned into particles. Okay? And again, what is a particle? It's a number. That's what a particle is, because you're going to put that number in an equation. So there is no real particle called a force, or a force called a particle. They're not equal. Force is a concept. Particle is like a grain of sand. That's not what it means in quantum mechanics. And unless you understand that, you're in deep trouble. Okay. So what happened? They had to find out why certain forces, they tried to unify these forces. They said, we have all these forces. We have the photon, which is the electromagnetic force. Now they had invented the weak force, which was this intermediate particle, or force, particle, whatever, okay, that creates the beta decay, or that mediates, or is an intermediate step in the beta decay. And then they had to hold the proton together. Okay, you had, and how do you do that? If you have three quarks, well, you got to hold them together. You have to have some glue to put them together, and that glue was the gluon. That's why they came up with the gluon. And so now you had these forces. The gluon is a force. The weak, the expulsion force from the atom, that's also a force. The electromagnetic is a force, and gravity is a force. And so the quest was on to unify all these forces. How do you unify them? So the first step was to unify perhaps the simplest of them, which was the electroweak, the weak forces with the electromagnetic force. The photon with the weak forces, and there were two of them, the W's and the Z's. Okay, and so these guys came around, I think 1970s, there's 1979, or I think that's when they won the prize or whatever. And they came up and they said, hey, look, if you increase the strength of them up to a certain point, at some point these forces will match. Okay, these, or as they say, the strength of the electromagnetic force becomes the same as that of the weak force. And so they did a calculation. They said, okay, it matches there. And then they went into the lab and they said, well, we confirmed it. Okay, fine. Now, what was the next step? The next step was the GUT, the grand unified theory. And they said, well, can we unify those forces? And right now, that's what they're working at right now. They're trying to make the accelerators more powerful so that they can create the necessary energies to unify those three forces. Okay? So these fellows won the Nobel Prize. Why? Because they were able to unify the electromagnetic force with the weak force. What does that mean? What have they done? What are we talking about in physical terms? That's the question I like to ask, because we're talking about physics, hopefully, right? And here, let me show you an example. Okay, you're going to unify the only two forces we know. One of them is push, and the other one is pull, because there's no other form of interaction, physical interaction we can imagine. So how these people came up with four forces, two of which are push and two of which are pull, and here you have it. You get rid of here. And here you have it. Okay, these are the push forces on the left. You got the photon and the weak force, and on the right you have pull forces, the gluon and the graviton. And yes, it gets complicated because the photon it goes back and forth between being a wave and a particle, and a stream of particles. The gluon is a little bed spring there. It's put as a bubble gum between the quarks, and we don't know what those gluons look like, why they look like that, how they are attached to the quarks. There's a lot of questions on the gluon. Why they turn into quarks when you stretch them too far, and so on. There's a lot of questions on the gluon. What is that gluon? Is it a particle? Is it a force? What is it? And then graviton, well, you can take your pick. You can go with particles, which is what the graviton is for quantum mechanics, or you can simulate it with a space-time canvas, trampoline. I call it the fishnet. Okay, so you can take your pick. I mean, how can you reconcile the graviton balls, the little particles, with the bending of space-time? You can't get, this is what they're trying to unify. They're trying to make these two equal somehow. And of course they're going to do it mathematically, or they're trying to do it mathematically. They can't do it physically, as you can see there. There's no way you can reconcile these two mechanisms, the particles versus, the canvas or fishnet. So that's the status quo today. We have the weak and the electromagnetic, in other words, the photon. We have those united at a given energy level. I think it's in the 200 giga electron volt range. You're going to need 10 to the 15th giga electron volts to unify those two with a gluon. And that's what they're working on now. They're trying to get the accelerators to get to those kinds of energies. And the other one is, at 10 to the 19th giga electron volts to get the graviton, because it's so weak at the atomic level, to unify that with the other three. So one is the gut, which is the strong force with a weak and a photon with a electromagnetic force, and the other one is the toe, the theory of everything, where you unify gravity with that. But what are they unifying? They're unifying energy levels. They're saying at a given energy level, we have the unification of all these forces. We're talking about a single force, or a single particle, because force is particle, particle is force. Maybe they're a field, the vibration of a field. Who knows what a force is, what a particle is anymore? Why is this important? It's important for them because they can unify that with general relativity. They can tell you that what happened at the Big Bang, or a couple microseconds after the Big Bang. Why? Because they say that's where you have the energies necessary to produce these forces and to split them up. As space-time expanded, all these forces branched out. One became the electromagnetic, the other one the gluon, the other one the weak, and the other one the graviton. So they kind of, each one went their own way. The only way you're going to get them unified is with the energies right immediately, microseconds after the Big Bang. So you see how this is all tied together. Quantum mechanics with general relativity. That's what they're trying to do. Okay, that's what they're working on. Now, the people in string theory, they've got a totally different version. They say, well, no, we forget about all of quantum mechanics. That's kid stuff. We don't do that anymore. We don't deal with gluons. We don't deal with quarks. We don't deal with protons and neutrons. We don't care about that. We're going to deal with the graviton and throw it inside a black hole and find out what happens, especially at the edges. That's the world of so-called mathematical physics, otherwise known as mathemagics. Okay, so here are the summary fatal problems as I see with quantum mechanics from a conceptual point of view. And these are just some of them. Believe me, I got a longer list than this. Okay, here's my list. Okay, just specifically for what I talked about today. Quantum particles, forces, and fields. What are we talking about? Well, the first thing is that particle is not a particle. A particle is a euphemism. Okay, it's a way of saying, look, I'm talking about a little bead. And as long as you don't ask any questions, I can put that bead and do traces and do whatever I want. I can show it the little particle going through gas, creating this trace, which is what I think that is, right? And so I can say, well, see, this is the trace of a gluon, and that's the trace of a quark or whatever. So that's when they use a little ball. And I always like to say that all they have to do is take a ruler, okay, and measure the width, right? To measure the width of the trace. I mean, if they got that trace, okay, we can figure out the diameter of these little balls, right? The gluon ball, which is what? A force. So I want to measure the width of the force, the diameter of the force. And I can do that really using their own stuff. I'm saying, look, if you say this is a ball that's going through the gas and creating this trace, which you've imaged somehow, very simple. Just tell me what the width of that trace is, and there you have the diameter of that ball. Very simple. It's like if you take a ball and you run it through, I don't know, molasses, right? And you leave a trace. Well, you can tell what the diameter of the ball is. It's just the width of that trace, right? So we can do it. It's just nobody is thinking in physical terms. They all just want to do math. Okay, fields. I showed the other day, they're all superimposed. Okay, and here, let me show that again one more time. Okay, we had all these fields, one on top of the other. Okay, and you have the background radiation, which is like a temperature field, 3 degrees Kelvin out there. Okay. You have all these fields, the electric field, the magnetic field, the electromagnetic field, the gluon field, all superimposed upon each other. And the question is, don't these fishnets somehow get tangled? Okay. So that's one of the issues on fields. What is a field? Is it a physical object or is it a bunch of numbers? So we need a definition or someone to tell us that a field is a physical object. One of the two. If it's, so if it's a physical object, please draw it. I want a drawing of it. I want to know what a field looks like. Okay? And if you're going to draw a fishnet, I want to know what the background that gives contrast to the fishnet is. So you got to identify that as well. And if it's a concept, well, then you can't say that a concept vibrates. You can't say that it's a bunch of numbers. Close to, like the gravitational field, you have the Earth, and the gravitational field extends outwards. Well, if that field is a bunch of numbers that get weaker and weaker as you get farther away, and you get the electric field and you have the magnetic field, and they are the same thing. They get weaker the farther they go out. You're talking about a magnitude at each point in space. That's a concept. You can't say that a magnitude vibrates or that a bunch of numbers vibrate. Okay, so this is the problem. A field is either a physical object, standalone, that you can draw and you can identify all the stuff that's there, whatever's on that picture, or it's a concept. If it's a concept, don't use it in physics. Don't tell me that you're going to vibrate a field and that a particle is a vibration of a field, because you're vibrating a number, and that's irrational. Okay? Then the next one here is the neutrino. Okay, we discussed that. Comes from the vacuum. It's energy that is borrowed from the vacuum. That energy is converted into a particle through E equals mc squared, where m supposedly stands in for the word particle, or the word thing. They're treating mass as a thing, when mass is not a thing. Mass is a concept, especially in the context in which they put it there, which is that E equals mc squared. If mass is equal to energy divided by c squared, velocity of light squared, and energy is a dynamic concept, we have a dynamic concept over another dynamic concept. That doesn't give you a physical object. So mass is not a physical object. It would be to some degree if you say quantity of matter, but that's not the notion they're using. The notion they're using is accelerate the thing and I'll tell you how much mass it has. So mass is a dynamic concept here, and it's exactly the same thing as weight. No difference whatsoever. Okay, conceptually. Okay. Quarks, what are they? Just an accounting procedure. I need 2/3 and minus 1/3 and all this other stuff, to account for why something has charge and the other one doesn't, and also helps me deal with mass. Perhaps even spin. Okay, the electromagnetic weak unification. What is that? That's just an accounting procedure. They're saying at such energy, we unify these forces. We unify push with pull. In this case, really push with push. It's two pushes. And they're going to have a little hard time, a little bit of a tough time trying to unify that with the gluon, which is a pull force. And not to mention the graviton, which is also a pull force. That's where I want to see how they unify those forces. Push with pull. Okay? Gut, toe, they're pull forces. Okay? How do you explain pull with particles that are not even particles, they're numbers? I need a physical interpretation. How do you pull with a particle? How do you pull on another particle? That's the issue. Very simple. Okay? Energy is not a thing. It's treated as a thing at all times. It's treated as a thing, especially in relation to with Einstein's equation, E equals mc squared. In other words, in relation to mass. Mass is taken to be quantity of matter for that split second. And people say, okay, I understand, mass is a physical object. No, mass is not a physical object, because mass is not, first of all, you can't make a picture of mass, period, we're done. But assuming we could say, okay, let's call it quantity of matter, mass is not the quantity of matter, or a measure of a quantity of matter. No way, no how. Mass, here, as it's used at the accelerators, is a measure of how much energy you need to push an ion or whatever you're pushing. So they look at the energy, how much energy is in that system, and that's how they determine the mass of that particle based on E equals mc squared. So mass is a dynamic concept. It's not quantity of matter. In other words, rest mass. That's not what mass is. Okay? Not in the context of what they do in quantum mechanics. Okay, so they've forgotten completely, they threw it by the wayside, the notion of quantity of matter. That's why, Wheeler and Taylor say, all those people who say that, mass is the quantity of matter or measure of quantity of matter, that number does not equal mass. It doesn't, because special relativity especially shows you that if you accelerate something, it increases in mass. Did it acquire more quantity of matter because it went at the speed of light? No, they're talking about pressure of the same quantity of matter. So if you accelerate let's say a neutrino, if you accelerate it faster and faster and faster, it has more mass, more mass, more mass. Okay, so if a neutrino walks a turtle space, it has a certain mass. But if you accelerate it to an eagle pace, then it has more mass. So it's a question of speed, of acceleration. It's got to do with something that is dynamic. Okay? And spin is not spin. It's not the top spinning. Okay, so this notion that they say spin and they insinuate that it's, the little ball spinning. And you say, okay, I understand that. The particle is a ball and it's spinning. That's not what it is in quantum at all. At all. So if that's the notion you have, that's the vision you have, is that what you visualize? You're visualizing it wrong. Neither do we have a particle, neither do we have spin. Okay, spin is more like a mark that you have on the top. And the top, you spin it, and if it points at you, we call that spin 1. If it points in the opposite direction, we call that -1. To the sides, maybe it's half minus half, maybe it's upside down, I don't know. So spin is not spin, and particle is not particle. Important to know. What have we learned? We haven't learned anything. Not from the mathematical physicists. Okay, we haven't learned anything because they don't have explanations. All they do is look for particles, invent particles really. They don't look for them. They invent particles to fit their preconceived notions. They look at something in the lab that they cannot answer. They see a phenomenon happen, and they say, how was that caused? What forces intervened? They go to the lab, they go to the office really, and they say, okay, I'm going to put a little particle in there that's going to represent some invisible force that intervened in this process, in this phenomenon. That's what they do. And then they look for it. Once they give values, they say, okay, look for it. And they say, well, how many giga electron volts does it have? Well, I don't know, 12. Look for something that looks like 12 giga electron volts. The guy looks in there and says, well, here's a trace. And this trace apparently has what we're looking for. It's got, it's a trace that requires 12 giga electron volts. And they say, okay, what are you going to call it? I'll call it Charlie. Here's your Nobel. That's how it works. That's quantum mechanics in a nutshell. Okay. Okay. Let's go with some of the questions. I had lots of questions this week. I don't know if I'm going to get through all of them. Let's find out. Okay, here's the first one. Fella says, what does he say? He says, Carl Sagan had hope for humanity, but he also was he was also a scientist, and he understood that things had to be proven. No, in science we don't prove. Okay, in science, the proof means you're doing religion. You believe, because that's what proof means. Some people have proven God and believe in God. Some people have not proven God and they don't believe in God. And so who's right? Well, proof is in the eye of the beholder. Okay, you are helping disprove any hope he had for humanity. Yes. I'm not a pessimist. I'm a realist. And when I say that humanity has no future, that we are the last humans on Earth, that's exactly what I mean. I mean that, there is no hope for humanity in that sense. There's no way we're going to come out of this. So, if the Titanic is sinking, I'd give you false hope if I say, no, don't worry, we're all going to be saved. The cavalry's going to be here or whatever. Or you're falling from an airplane without a parachute, and don't worry, it's soft down there. You're going to fall in the water, or you're going to be okay. No, let's be realistic. You're going to fall on the ground. You're going to kill yourself in a microsecond. You're not going to be around. So, to say that, give you hope, false hope, at least I don't do that. I like to say it like it is. And I'm going to tell you always that we're the last humans on Earth, or the last generation of humans on Earth. We got very little time to go. Okay, next issue. Way at the bottom, we got to get them up here. Our reality is exposed not by science, but by simple philosophy. The source is beyond our senses. Well, see, this is the problem with religious folks. They want to use their senses to sense. And the only sense they need to use is common sense, the least common of all senses. And so religious folks say they've given up hope. They say, we're not going to understand how this universe works. All we can do is philosophize and, believe. So that's not science. Science is, give me an explanation, an objective mechanism of how gravity works. And that's not philosophy. That's giving me a mechanism. You give me one mechanism, the other guy gives me another mechanism, and maybe I come up with a third. And then we compare notes, we all understand, we go home, you believe whatever you want at home. But at the conference, we just exchange mechanisms so that we understand and we enrich science. We have all these different mechanisms from which to choose. Okay, then you choose whichever one you want. Okay, and here's a corollary to that, I guess. I know this is another fellow who more or less a corollary, says, we cannot see small enough, so we do not know if we are correct. We know we are correct up to the scale that we can see, and that's it. Again, people believe in knowledge. People believe in correctness, what's truth, what's false, what's wrong and right. None of that has anything to do with science. It has to do strictly with religion. We don't use knowledge because knowledge is belief, justified true belief as Plato defined it. It still is the definition of knowledge. It's belief. Anyone who knows for sure, for a fact, is believing, period. Okay, so we don't deal with knowledge in science. And we don't deal with correct, incorrect, true, false, right, wrong. That's all religion. Okay, that's your personal interpretation. Okay, personal belief. And then it says up to the correct scale. Science is not about scale. It's not a question of accuracy, of precision. It's got nothing to do with that. That's mathematics. In science, we have to explain the mechanism. I got to know why this pencil falls to the floor. That's it. I got to explain that mechanism. That's what science is. Accuracy has nothing to do with it. Precision has nothing to do with it. It's not, when you talk about accuracy and precision, you're talking about math. You're talking about an equation that describes that. We don't care about that. We want a mechanism. Okay, that's physics. Okay, and C, the word C, that has to do with senses. Again, we don't use our senses other than common sense in science. Okay, we have to be rational, and rational means you're not going to move a concept, which is what mathematical physics does. All they do is move concepts around. They transfer energy, they move the mass, they wave the wave and stretch the field and so on. Okay, Kandarope explained a double slit experiment and light speeding up after leaving a transparent, dense medium. Well, I've explained that several times already. There are a couple videos out there. I'm just going to quickly summarize here, okay? Here you have the double slit experiment. You can see how the rope explains it. All atoms are interconnected, so all we do when we turn the light on is stimulate the existing ropes that are already connected from the flashlight or whatever source through to the partition that has the slits to the screen behind it. Okay, so all those atoms are already connected before we turn the light on. As soon as we turn the light on, all we are doing is increasing the frequency. And as far as coming out of the dense transparent medium, here we have, if I can put it up here, prism, okay? And the rope explains it. I've explained this in the past. All we don't have a difference in speed. All we have, light always travels at c, okay? Because it's the equation of a rope is c equals frequency times wavelength, and all we're doing is changing the number of links and the length and the the length of the link. In other words, how short or how long a link is. That's all it is. But anyways, that's explained in a separate video. I'm not going to go in detail here. Just got to look around. Maybe look it up, in YouTube. Okay, with my name and the videos that we did. Okay. Fellow says, I drew a square on a piece of paper. Is the square an object? Yes. No. Of course. No. Okay. Obviously, your definition of the object is too simplistic. It lacks additional attributes. Okay, so let's answer that. Yeah, what this fellow is using is, or what he's using by default, okay, is the notion of ordinary speech. He has been drilled throughout his life that an object is that which you can touch and see. And those are the attributes he assigns to this. So he says, if I draw a square, is that a physical object? And for the purposes of physics, it is, because it meets the definition. First, the word physical is a synonym of object, so you don't have to say physical object, but I like to say it so that it hurts your ears. That's the only reason I use the term physical object, because I want you to, when I look at a triangle, I want it to hurt your ears when I say that's a physical object. And you say, what do you mean a physical object? Physical, isn't that what we touch or see? No, that's the notion of ordinary speech. In science, in physics, an object is that which has shape. That's the only property it has. And the fellow says, hold it, you're missing a lot of attributes. Yeah, because none of the other attributes are universal. The only attribute that's universal, all objects have it, is shape. That one you can bet your life on. A square has shape, a triangle has shape, Superman, Snow White, they have shape. All those have shape. It's got to be a standalone shape, okay? Field has shape only because there's something going on in there and you can sprinkle iron filing and say, well, that has shape. Yeah, but see, you need to be able to bring the field alone to the conference. You should be able to put the field all alone in space, nothing else in the universe except a field, and point to it. And a field is a dependent object. It depends on something. You need to bring the magnet. You can't bring the field. You can't bring the field without the magnet. You need the magnet. That means it's a dependent object, like the halo of an angel. If you just bring the ring or a plate, well, that's not a halo. In order for it to be holy and be a halo, you need to bring the angel. Then it has meaning only in that sense. Okay, and same thing with a field. Field is a dependent object. So if it's a dependent object, it's not an object. It has to be independent to be an object, standalone. And it can't be moving because, again, motion can only be performed with respect to some other object. So no, the universal property of all objects is shape, form. And shape and form are synonyms. There is no difference between shape and form in science. Oh, in ordinary speech, yes. In religion, yes. In science, in physics, form and shape are perfect synonyms. You can use either word. Doesn't matter. Okay, so this notion that you bring from ordinary speech that form is 3D and shape is 2D, no, that doesn't work in science. Okay, you can't distinguish those two. In fact, like I always say in Spanish, we don't have a word for shape. We use the word forma, which is just form. Okay, and probably other languages have the same thing. There is no word for shape. Okay, there's synonyms in, at least in Spanish, probably in other languages as well. Okay, I don't believe in fields, therefore I have the right to ask you again, how do your ropes avoid tangling? Okay, I like that. You don't believe in fields? What do you believe in? God, ether, waves? You got to tell us what you believe in, see? In science we don't believe. In science we propose what is known as hypothesize. We make an assumption of what invisible entity, what secret agent Mother Nature has out there with which she does her gravity, her light, her magnetism, all this other invisible stuff. And so we propose an object. It's better be an object. Can't be a concept. If it's a concept, well, then you drank too much. Okay, so you cannot use a concept. You need to have an object, and you can't say there's nothing there because you can't see or touch it. Because again, an object is not that which you can see or touch, and that you can test in the lab through an experiment. An object is that which has shape. Okay, and so no, you don't have a right to ask again until you tell us. Because see, science is not about criticizing. Science is about proposing. You have to propose a mechanism. So first tell us, show your hand. You can't hide your hand and say, oh, I'm going to keep my hand, but tell us how the ropes avoid tangling. Well, how do the fields that you believe in probably avoid tangling? How do particles avoid colliding? I mean, we collide them inside the accelerators, right? So obviously these particles apparently have surface, right? And you're colliding them, you're hitting one against the other and breaking them up or whatever, okay? So obviously they don't go through each other, right? So how do all these particles, when I shine a light against another, two lights and just cross them, how come the lights go through each other? That's what you got to explain. I mean, don't those particles collide? Shouldn't I get all this bouncing around of particles? Like, when you take two showers, two of these showers that you, or two sprinklers, and you see the water droplets. If they are in the path of another water droplet, they'll hit each other and they'll bounce out. You'll see some splashing there. Okay. In fact, you don't need another shower. You can put yourself there and you'll see that the water just hits you. So the water's there and it collides. But that doesn't happen when you put two flashlights against each other. The photons don't collide. Okay? Even though Burke, one fellow out there, says they do, he used virtual particles to explain that. Okay, so I've addressed that in the past. Anyways, you got to tell us what you believe in. What do you believe in? Fields? Do you believe in waves? Do you believe in particles? What do you believe in? And how do those avoid colliding? How do those avoid tangling? That's the first question you got to answer. When you answer that, we'll answer the tangling. How's that? Okay. So again, they avoid tangling because tangling is not a property of the ropes. That's why they avoid tangling. An object is not that which tangles, which touches. An object is that which has shape. And it takes 2 years for a person to understand that. Because if it has shape and it doesn't have the property of touch, okay, then you don't have to even bring up the issue of tangling. Okay, so that's where you got to start. Okay, another comment. Got a lot of these this week. They're getting more. Pretty soon, I won't be able to cover them all. These particles exist for so short an amount of time, popping into existence. He's talking about the particles like quarks and neutrinos and so on. Then annihilates with an antiparticle, that it doesn't experience the effect of gravity enough to contribute to its weight, as well as the particles being so small that the graviton likely misses them. So we have a problem because, first of all, we don't know anything about gravitons. Then I want to know what these particles and antiparticles look like. In other words, what's the difference between a particle and an antiparticle? I mean, do they have a different structure or what? I mean, this is all we know so far when you say particle and antiparticle. Is that a particle, a number with a plus sign on top of it, or another number with a negative sign on top of it? Is that what a particle is? I want to know what a particle looks like and how an antiparticle is different than a particle. In shape, in looks, I want to know what these particles look like. And of course, you won't find that anywhere in the standard model. You will not find what the gluon looks like. In fact, if you go to the standard model, you'll find out exactly what it looks like. It looks like a letter G, a little letter G, because I think the big letter G is reserved for the graviton. So what did the W bosons look like? They look like a W. How about the Z boson? Well, they look like a Z. So you don't have shapes for these particles. I thought they knew what they looked like. I mean, haven't they smashed these particles? Don't they image them inside their colliders, or when they put them on a computer, they image these things? I want to know what a gluon looks like. And then they have these bed springs or bubble gum stretching. Is that what a gluon looks like? It looks like bubble gum? So first tell me what they look like. Then you can talk about, annihilation and all this other stuff. The other issue is, if they come in from the void and you don't have to explain the void, you just say, well, it's full of energy, it's full of particles, virtual particles, and they come in when we need them, then they go back. Well, that's magic. That's like they're leaving open-ended the source. So you don't have to explain that part, because you just say, well, we don't know. It's like the curtain moves inside my room and I say, oh, that was what happened there, and I say, well, what happened there was my great-grandmother. She comes in every now and then, moves the curtain. Oh, okay. I was scared there for a moment. I thought it was a ghost. So no, you gotta, anybody can explain something. If you bring magic, you say the particle just comes in from the void and then goes back. That's known as magic. That's known as black magic, not as science. And that's what quantum mechanics is doing. They're inventing all these particles, just bringing them from the void. Because that way they can say, well, the void is made out of something, and then we bend the void, and that's gravity in general relativity. Okay, here's another question or comment. It says, I don't understand how you can question things such as mass. Okay, no, I'm not the guy questioning, okay? I want you to know that I'm not the fellow who's questioning. The guys who are questioning are these two fellows, okay? Wheeler and Taylor, and they say, nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass. So mass is not the quantity of matter. These people are questioning it. Please answer them. Okay? Don't ask me. Ask them. What is mass? Is mass matter, quantity of matter, or a measure of a quantity of matter? Taylor and Wheeler say no. They should know. I'm sure they outrank you a little bit. Okay? By a little bit. Okay. Another comment. I think same fellow, says, yes, kilogram is a measure of atoms. Each atom of any element, say hydrogen, experiences the same gravitational force and so gets pulled down equally. Okay, that's Newtonian version. You go to good old Einie there, and he says, you are being constantly pulled down by the curvature in space-time. These two comments came from the same fellow. So he doesn't realize that he's got a contradiction. Okay. Either we're dealing with force or we're dealing with bending of space-time. which is true. And he doesn't realize it. He just regurgitates what they put in his head, the brainwashing. He just says, yeah, it's a force, gravitational force. And then he goes over here and he says, well, yeah, it's a bending of space-time. Again, you got to tell me, what is gravity? Which one is it? Which one is mass? Is mass what bends space-time? Is that the way we're going to define it? Why does it bend space-time? Why does it bend space-time upwards? That's what I want to know. Why didn't Newton's apple fall towards the sky? That's what we need to figure out, okay? So you got to tell us what gravity is and what mass is. You can't just say, well, for Newton it was a force, and for Einstein it was warp space, and we're okay. They reconciled, they shook hands, drank champagne, both got a Nobel, and let's continue. No, you got to tell us what it is. You got to tell us what mass is, not what it ain't, okay? And what force is, what gravity is. You got to explain these mechanisms, okay? The other cords that connect the astronauts' atoms to the universe are missing. What do the ropes of the sun do, and that of Jupiter, and those of the Andromeda galaxy? What are they doing? Don't they pull? First of all, ropes don't pull. And I don't know how many times I have to answer that question. Ropes don't pull. Between two atoms, there is tension. That tension is constant. That's why c, little c, velocity of light, is a constant, because it only exchanges frequency in exchange for wavelength, and vice versa. Okay? So when one is short, the other one is long, or many. In other words, when wavelength or link length is short on a rope, okay, here's the example, okay? When the links are short, I'll twist this, okay? You get lots of links, okay? And when the links are long, you have fewer links. Okay, so that's it. And so that's the tension on the rope anywhere in the universe, between any two atoms. Okay, so that's tension, not pull, but tension between any two atoms. So gravity is an aggregation of ropes, okay? So here I put this example based on what he just said. He says, look, don't the ropes pull on the astronaut. There you see the astronaut almost falling onto space on the lower right. And the moon is 1 light second away, a little over. Light second, about a light second and a quarter. And Venus, when it's at its closest approach to us, which is about 41 million kilometers, at that point, it would take 137 light seconds. So you can see that Venus is much farther away than the moon, okay? And so you can see what's happening to the ropes. The farther you go, the ropes merge and form almost a single coaxial. And that's why gravity is so weak from far away. Gravity is only strong, like when you see there the astronaut, you can see the ropes connecting him to the earth, a little piece of it, okay? And they fan out. That's the difference. The difference is the fanning out. The closer you get to another object, the ropes fan out. So no, it's not an issue of how many ropes are connected to the astronaut, because all the ropes in the universe are connected to the astronaut. But the question is, how does distance play a role in that phenomenon, in the phenomenon we call gravity, okay? Okay, another fellow says, Jesus, they really swamped me this time. Okay, let's read it out here. Let me get back in. Says, your analogy is not adequate. Certainly the mountain climber on the rock would feel the weight of the rope connecting the hanging man. It's just negligible and not zero. Yeah, well, we agree. If you see this analogy, it would mean, if you use this analogy, it would mean that your ropes are not weightless, but surely very light. Okay, what is he talking about? He's talking about this analogy of the mountain climber that I used the other day, okay? And it is that if a mountain climber is hanging from another mountain climber, essentially the weight is of the mountain climber that's hanging, not of the rope that interconnects them. That's more or less the notion that I want to give here for the ropes. You have a rope connecting two atoms, one two-dimensional, the other one three-dimensional, just for the sake of illustration. And the rope, one atom feels the other atom. It doesn't feel the connection between them, okay? But obviously, the atoms are made of the same thread as the rope, okay? So if they're made of the same thread, you could say, yeah, the rope conceptually, right? Conceptually has weight, has some, it's matter in that sense, okay? But the question is, can you weigh this thing? And first thing I want to say here, give me a second here. I did mention that in that video. I said even though the rope does obviously have some weight, and what I was referring to there is that we cannot weigh the rope, but conceptually, from a conceptual point of view, the rope is made out of matter because it's made out of the threads. And you could say that the threads are part of the matter of the universe, whether they form a rope or an atom. So there's really, in that sense, you would say that it does have some weight. But, here's trying to weigh them. Here's weighing the atom, okay? And there's the rope. I don't know if you can see that on the right, okay? You're talking about, and I'm being kind to the rope there, because really the rope is much thinner with respect to the atom that is, as you see there. So you're talking about something very light, very thin, and you're never going to be able to weigh it. When we talk about weight, we usually talk about atoms and upwards. We don't talk about something below that, except in quantum mechanics, where they don't talk about mass. They really talk about weight, and that weight is calculated through energy. Energy equals mass times velocity of light squared, meaning weight times velocity of light squared, because what they're doing is accelerating the particle to determine how much energy it has, and then they calculate what they call mass, which is weight. They're not looking at how many particles comprise the neutrino or the quark or the proton or any of that. No, they're looking at acceleration. How much energy do you need to accelerate this? Well, we turn that into mass through E equals mc squared. That's how it's done, okay? So the so-called mass used in all, here on Earth, anywhere on Earth, is never quantity of matter. It's always weight. What do we put in Newton's equation? Force equals gravitational constant G, mass divided by distance squared. What do we put for the two masses? We put weight. We weigh the apple, we weigh the elephant, that's what we put in there, and then we calculate force. We say, well, the elephant had 5,000 kilograms of weight. They call it mass, but it's called weight. And how much did the apple weigh? Well, it weighed so much, a few ounces. Okay, fine. And now what you do is you calculate the force between the elephant and the apple, and that's the force, which is weight. So you say, how much does the apple weigh if the elephant were the earth? In other words, with what force of attraction would there be between the apple and the elephant if I use Newton's equation, like outside of the earth in the middle of nowhere? And yeah, that's what it is. What you're looking at is weight. There is no such thing as mass. Mass is only a definition that they say quantity of matter, and then they never use that again. What everybody on earth uses is weight. Okay? Nobody uses mass, because mass means quantity of matter. We don't count atoms. We don't calculate, how many atoms there are in the Grand Kilo in France. We don't do that. It's always weight, always weight, weight. 150% of the stuff that we've ever done is weight. Never have we used mass. Okay? Nobody knows anything about mass on planet Earth. Maybe you're from a different planet that's different. Okay? So let's make sure nobody uses the word mass. Everybody uses weight and calls it mass, okay? Because mass is supposedly a measure of, weight is a measure, mass is a measure of a quantity of matter. Okay, another question here, another issue. Fellow says, how can ropes exert pull on two atoms they connect? See, if this fellow would have read the book, which is free, downloadable, you can just go there and find the book, he would have found this. He didn't realize this. You know, I already came up with the stuff way before him. Here it is. Okay, Charlie cannot pull on both Andy and on Bob. He either pulls on one or he pulls on the other. Okay, so if Charlie just holds on to the rope, he's irrelevant. He doesn't count as mass. The only way you're going to feel Charlie is if he goes out of alignment, pulls the rope out as you see on the bottom right there. Okay, then you're going to feel Charlie. Otherwise, you don't feel Charlie because he can't pull on both Andy and Bob. So the rope doesn't pull. That's the issue. So it's this word pull that's got everybody wrong, because gravity is a pull force, we say, but what is happening is not really a pull. What is happening is a drift. It's drifting in proportion to distance, inverse proportion to distance. As the astronaut falls closer to the Earth, the ropes fan out. It's the same number of ropes pulling on the astronaut here and there. But here, because of the distance, the ropes fan out, and so now all the atoms are no longer in a single line on the same axis. When that astronaut is out there in the middle of nowhere, all the ropes come together and they're almost on the same axis. And again, you're talking about atoms which are vanishingly small. So all those ropes come together. And suddenly, you know, when that guy comes close, the ropes fan out. So there is no pull on the ropes between any two atoms. It's a question of distance. How close the astronaut is to the Earth, that's how much the ropes fan out. And that's what causes the acceleration of gravity, which we call pull. Okay, but there is no pull. All ropes only have tension measured by the velocity of light. Okay, that's the constant tension on the rope, the velocity of light. Okay, another comment. I think this is the last one. And then I got some homework for anyone who cares, related to mass. For those of you who are experts in mass and want to talk about mass, okay. The hammer and feather, their masses as well as weights are different. Is that true? Is there a difference between the mass of the feather and the hammer and between the weight of the hammer and the feather? Let's find out. Okay, here we have the hammer and the feather. Okay, and you can see that they both fall on the moon. For those who believe that we went to the moon, they fall at the same time on the ground. So from that experiment, we cannot tell whether the feather or the mass weighs more than the other. Okay, or what mass each one of those has. It looks right now they look exactly the same. Okay, because they both fall at the same time. And you can see it here on Earth on the picture on the bottom right, but on the left picture there you can see that both the feather and the piece of metal fall at the same time because there's no air in that container. Okay, so from those experiments you cannot tell the difference between the feather and the hammer. Okay, now here you have what I showed the other day, which is an elephant and a hammer falling towards Earth. Okay, and again, if you let go of them, they fall at the same rate. And out there in space, you cannot tell the difference between the mass or weight of the elephant and the hammer. You suspect the elephant has more mass, but right now that's intuitive. You can't really prove it there. You can't prove it to yourself. You can say, well, it looks like they have the same mass, the same weight. Okay, how would you prove it? Well, you know, here it is without motion. Okay, they're out there in the middle of nowhere. Which one has more mass? Which one has more weight? Can you tell me by looking at that picture? Okay, that's the issue. And no, so right now we can't. Until you tell me what mass is and what weight is, and you can tell me how you're going to determine the difference between those two, mass and weight, scientifically, not mathematically, okay? I need to know what the difference is between mass and weight. Right now we don't have a definition of mass. In fact, if you take the grand kilo, like I say, from France, and you take it to the North Pole, and you take it to the equator, you're going to find that they have a different weight. That same standard in the North Pole at the equator has a different weight. And you say, see, the weight changed, but not its mass. Well, how did you determine mass? Well, you weigh it. That's how you determine it. And so, yeah, its weight changed because its mass also changed because we determine mass by weighing. We've never done mass here on Earth. We've always done weight. And we do weight in special relativity, and we do weight in quantum mechanics. Everybody does weight. Nobody does mass. So we don't know what mass it has. Anything has, for that matter. You know, it's always weight. We weigh it. And that's what we put in Newton's equation also, as I said before. Okay, okay, here's the homework. Anyone who wants to try it, here you have it. Okay, homework, okay, for everybody. See, all the experts in mass, so everybody wants to talk about mass. Okay, here you have the chance to talk about mass. Okay, we have one astronaut. It's the same astronaut. Okay, and he's going to be weighed at different distances from Earth. Okay, so we have this thing up there, and we put the scales there. Okay, we're going to weigh the astronaut at one distance, and then at a different distance. One is closer to the Earth, the other one is farther away from the Earth. That's the setup. That's all you need to know, okay? Now here are the questions. These are the questions that you need to answer. There's 3 questions you need to answer. If you're smart enough, you can answer them. If you're not, well, sorry, your mama didn't give you what you needed. Here it is, okay? So here are the questions. Does the astronaut have a different weight at each location? Yes or no? Just a yes or no. I don't need any numbers. Please do not put any numbers. We don't need any numbers. We just need to know if one astronaut weighs, it's the same astronaut, by the way, okay, once again, okay. I just need to know if they have different weights at these 2 locations. If so, which astronaut weighs more? Which one would push down on the scale more, or which one would the scale show a greater value? Would it be the one on the bottom or the one on the top? Very simple questions, I think, okay? And then the third one, which is really the key issue, why does the astronaut weigh more or the same? Okay? I need to know a cause, a mechanism, no numbers, no calculations, no descriptions. He who says that because of distance or because the acceleration of gravity at that point will be treated as an idiot because he doesn't realize the difference between a description and an explanation. The explanation is the explanation of a mechanism. We need to know the cause. We need to know why. What causes? Okay, what is the mechanism that causes the astronaut to weigh more or to be the same at these 2 distances? That's all you got to answer, okay? So put your comments down for next time, and I'll address them, as long as you don't say that's because of distance or because the acceleration of gravity is the same at different at these 2 points. We don't care about any of that. Those are descriptions. We need an explanation. We need a physical cause. We need to know why, okay? So there's your homework, and